I'm Geert Raaijmakers. Sorry. I'm a PhD candidate at the University of Amsterdam. And today I'm going to be talking about equation of state constraints from NICER and multi-messenger observations. And this is sort of talking about work that I've been doing in the last few years of my PhD. Also with a lot of help from some of the team members that are mentioned at the bottom here. This is really a team effort. So let me start with like a brief introduction. This is probably not really necessary for the people in the audience here, but just to sort of get the general idea, what we want to learn about is we want to probe the neutron star interior. So if you have this basic picture of the neutron star, we have the outer crust where we still have some ions structured on a lattice. We have free electrons flowing through. Moving deeper into the neutron star, the density increases, and at some point electrons will interact with protons to form neutrons. So you get more neutron-rich nuclei, but also as you increase the density even more, at some point neutrons will start to drip out of these nuclei. So you will get sort of a sea of free neutrons, some electrons, and some nuclei still in there. And so that's sort of the outer core of the neutron star. And if you then reach the most dense part of the star, this is really where we don't have a clear understanding anymore of the behavior of matter. So you can still have superfluid neutrons, superconducting protons, just normal nucleonic matter. But you can also expect maybe some more exotic phase transitions to quark matter, or even hyperonic matter may start to appear. And so this is really the region that we try to probe, and I've been trying to probe during my research. And so what we really want to, what we're really interested in is actually to probe this phase diagram. So this is the QCD phase diagram. So it's sort of describes the strong interaction, and we sort of fill in this phase diagram by if you go to very high densities, then you know that at this point you have quarks that are in a free state, so free quark matter. If you go to very low densities, that's sort of the regime where we are in, so where quarks are confined inside hadrons like neutrons and protons. You can sort of probe this with heavy ion experiments, but those are generally a little bit higher temperature and lower density. But sort of a really big part of this diagram you can only probe with neutron stars, and so you can see the cold neutron stars, which I'll be talking about mostly, sort of nicely follow along the zero temperature axis. You might start to probe this phase transition, going from quarks confined in hadrons to free quark matter, and then also I'll be mentioning briefly neutron star mergers, which potentially are very interesting to sort of probe a little bit higher densities and a little bit higher temperatures. So you can maybe see this phase transition there too. So how do we connect these like very small scale physics that we're interested in? How do we connect that to things that we can actually observe? I'll very briefly talk about this connection. So we know that this information about this behavior of matter is encoded in the equation of state, so this pressure density relationship. We can calculate the mass and the radius, and also, which I didn't plot here, the tidal deformability of a neutron star from that using the relativistic structure equations. And these are things that we can actually observe with things like NICER. I believe this is the Virgo detector, so gravitational wave detectors. And I'll talk a little bit about this process of how do we get the mass and radius in the context of NICER. So we've heard a little bit about this, I think, on Monday, also from Serena. But so to introduce this again, maybe in the context of my research, so we're working with NICER data. NICER is this neutron star interior composition explorer, launched in 2017 and installed on board of the International Space Station. You can sort of see you can see a nice video here of NICER sort of dancing around, pointing at different neutron stars. And this instrument is measuring the energy and the time of arrival in sort of the soft X-ray band. And it's specifically looking at rotation-powered millisecond pulsars. And these are particularly interesting because what we think is that near the where the magnetic field lines sort of go through the neutron stars at the magnetic poles, you expect some of the positrons from the magnetosphere to sort of hit the surface of the neutron star, heating up the surface in these spots, and this will emit thermal X-rays. And so this is what NICER is sort of observing, and this allows us to do something called pulse profile modeling. So in the plot here on the lower right, I'm showing the energy versus the phase of the pulsar, and you can see this very nice pulse behavior that encodes some of the information that we eventually use to get the mass and the radius out. So maybe let's see if this is playing. Okay, not really. This is a video, but it works as well as an image. So this is actually the same neutron star. So on the left, this is sort of where we turn off the special relativistic corrections. So we call this no gravity. And on the right, we have the same neutron star, but where we sort of turn on general relativity, and we can immediately see that we can see a much bigger part of the surface of the neutron star. And so below here is the brightness of these X-ray bright spots on the surface of the neutron star. And so as the star is rotating, this spot is going to move in and out of the field. So on the left here, you see that it sort of brightens and then it disappears when it's behind the surface of the neutron star. Whereas on the right, if we do include some of these general relativistic effects, as the neutron star is moving around, this pulse, this hotspot actually never really moves behind the surface of the star. And so you see that this pulse profile looks very different if you have these relativistic corrections. And this is interesting because most of these effects that affect this pulse profile are going to depend on the gravitational field around the neutron star. So they're going to depend mostly on the compactness of the neutron star. And so by doing some ray tracing, you can actually say something about the compactness of the star, and by using some of the other effects, you can break this degeneracy and say something about both the mass and the radius of these stars. And so far, NICER has done this for two different pulsars. So I've plotted them here, mass versus radius. The first one was J0030. It had a radius of around 12.7 kilometers plus or minus 1, and a sort of vanilla neutron star mass of 1.3 solar masses. And then more recently, NICER also measured the mass and the radius of JU740, which was interesting because it's actually the most massive pulsar that we know of. So it has a mass of 2.07 solar masses, and this was independently already constrained from radio timing. And it had a very similar mass of around 12.4 plus or minus 1 kilometer. And so this is sort of where we're currently at. These are the two measurements that NICER has published so far. So from there, let me move on to more the research that I've been doing these past few years is, what if we have these measurements of mass and radius, how do we translate that to actual measurements of the equation of state? And ultimately, even go beyond that and say something about the microscopic behavior of particles at these extreme densities. So let me first start by just overplotting the NICER results with a lot of theoretical models for the equation of state. So this shows a very large variety in different models. So you have some pure quark stars, you have models that include very strong phase transitions, normal nucleonic models. But what you sort of immediately see is that the NICER measurements do exclude some of these models just by looking at their credible regions. But we want to do something a little bit more sophisticated. But we can't really do that with these individual models because they're all, most of them are computationally too expensive to sort of generate on the fly in some sort of parameter estimation. So what we usually do is we use some parameterized version of the equation of state, so that we can actually constrain the equation of state parameters that describe that model. So we want to learn the posterior on these equation of state parameters. I'm just quickly repeating Bayes' theorem here. So this is proportional to the prior on these equation of state parameters multiplied by the likelihood. And here the likelihood is coming from, in this case, from these mass and radius posteriors that NICER is actually measuring. So what we're doing is using these parameterized equation of state models, and to get a little bit of a feel of some of the systematics that we have in our modeling, we're using two different models. So on the left here is a piecewise polytropic model. This is actually quite widely used in modeling the equation of state, and this is simply put, you just divide the equation of state in the density space up in different parts, and each part is modeled by a single polytropic function. At lower densities, we couple this to some calculations of neutron matter using color effective field theory, and then at even lower densities, we connect it to a cross model. Now, the piecewise polytropic model has some issues because at each of these transition densities, you'll have some discontinuity in the speed of sound that doesn't really come from anything physical. And so we're also using a speed of sound model where we at least know that the speed of sound throughout the equation of state is continuous. And so it allows us to put a little bit more of a physical model in. And same for this model, we connect it to these low density calculations from chiral effective field theory. I just want to mention quickly that there's different ways of sort of approaching this. So we're doing these equation of state parameterizations, but recently also people have been doing more discrete sampling of a pre-computed set of equations of state that gives you a little bit more of a handle of the prior actually in the mass radius space, and also quite popular recently is doing these non-parametric equation of state inference where you use something like Gaussian processes to be a little bit more model independent in your equation of state constraints. Okay, so let's then go to the data. So we're using three different types of data. So first, we're using radio timing, and radio timing gives you actually extremely nicely measured masses of neutron stars. So the most massive one, as I mentioned, is JO 740 with a mass of 2.08 solar masses. We're using gravitational wave signals that encode something about the tidal deformability of the neutron star. And so far we've only measured two of these binary neutron star systems. So 17817, of course, the very first binary neutron star gave us a lot of information on the tidal deformability actually. And then we also include 190425, which was a little bit lower signal to noise event, which actually didn't give us that much in terms of equation of state constraints. And then, of course, as I mentioned, the mass radius results from NICER on JO 740 and J0030. So I'm gonna, in the next few slides, sort of go through these step by step to really separate out the different, how each of these measurements is contributing to the constraints that we currently have on the equation of state. So I'll be showing a lot of these plots. So this is basically showing our posterior distribution in the mass radius space. So I'm plotting mass versus radius. For the green contours, the darker region is the 68% credible region, and the lighter green is the 95% credible region. And so the first one that I'm showing here is what we get for the when we just include the mass measurement coming from radio timing. And so this is from JO 740, again, roughly 2 solar mass measurements. In black, we show the prior distribution, so the 95 credible region of our prior distribution. And then you can sort of ignore the orange one here, but focus on the green one. And we can see that just this radio measurement is going to already cut down your prior by quite a bit. And so you see that that is really pushing you already to the edge of your prior region, actually towards very stiff equation of state. Then if we turn to gravitational waves, here in orange, I'm showing the results for 17-rate-17. So 17-rate-17 was sort of favoring quite, it put an upper bound on the tidal deformability of neutron stars. And as such, it was sort of preferring much more softer equations of state. So you can see that it's the posterior distribution is also pushing you towards lower radii. Then in blue here, I'm showing the results that we get for 1904-25, and it may seem like this is actually giving us a lot of constraints, but 1904-25 was also a very massive system. So because we haven't assumed anything about the neutron star mass here, just by having a very massive system, you're going to cut down on this prior region as well. But in terms of tidal deformability, it actually didn't give us that much information. And then in green is sort of the combined posterior distribution of the two gravitational wave events. So sort of the takeaway here is that in general, the gravitational wave constraints are pushing us a little bit towards more softer equational states or lower radii. I then move to the nicer results. So this is in orange, this is the measurement from JO740, now not just the mass, but also the radius measurement of nicer. And in blue is the measurement from J0030. You can see that J0030, because it was such a sort of vanilla mass neutron star, the constraints weren't too, it wasn't too constraining on the equation of state, whereas constraints from JO740 were much more, well, you can see it's much more constraining, but again, this is due in large to sort of the very high mass of this particular system. And then in green, this is the combined analysis, and you see that it's quite close to just including JO740. And then finally, if we move to sort of the whole, including all of the data, so this is our multi-messenger contributions. In green, this is in orange, this is sort of all the previous measurements that we had up until JO740, but including the mass measurement of JO740. And in green, I'm showing the posterior distribution when you do include the nicer radius measurement on JO740. And you see that you improve a little bit on your constraints, but actually the radius constraint from nicer didn't add too much on your posterior distribution. What you can also see is that for the speed of sound model, we're really pushing actually towards the edge of the prior. So this really high mass neutron star is sort of pushing us against the limits of this model. So one thing that we wanted to investigate a little bit more is what is actually the influence of this low density calculations that we're using. So these chiral effective field theory calculations. So what we did was we tried to get a feel of the systematics that we got from choosing a particular set of calculations, and we compared actually 4 different approaches to this. And so here in the upper right, you see calculations from 4 different groups of this low density regime. We approximate each of these uncertainty bands with a single polytrope in this region, and then we rerun our analysis. And so here in this lower left plot, you sort of see the differences in the posterior distribution. And we kind of estimate that just by fixing to a particular set of computations, we get an uncertainty of the order of 0.5 kilometers, especially at lower masses. Now, interestingly, if we actually exclude this low density calculation, but instead directly put our high density parameterization on top of the cross model, you get the posterior distribution here in the red. And you can see that this actually allows for much higher radius. So we can see that this low density calculations really constrain the higher radius part of our parameter space. Now, one of the interesting things about the NICER results was that we have two different radius measurements so far. One of a sort of 1.4 solar mass neutron star, one of a very high mass neutron star. And so what you expect maybe is that for the very massive star, the density in the core is much higher. So maybe at that density, you actually start to see something from this phase transition. But a phase transition would normally give you a lower radius. So it was quite surprising me that the radius of JO740 was actually very similar to J0030. Now, I'm just showing this plot here on the right, which is from a paper by Christian and Schaffner Bielig, which sort of looked into this and asked the same question: is a phase transition actually still possible? And their conclusion was, so these purple lines here all are equations of state that do have some sort of phase transition. And their conclusion is it's actually still very much possible to have a phase transition in this more massive star. And the uncertainties in the mass radius measurements currently are not enough to sort of rule that out as of yet. So briefly, an outlook on what more we can expect from NICER. So interestingly, there's still going to be more follow-up on J0030 and JO740. So this is definitely not sort of the end of this story. They might still give some very interesting results. Very exciting also is this other pulsar JO437, which has an independently measured mass of 1.4 something, but it's very tightly constrained and it's a very bright source. So this might actually give you very tight constraint on the radius as well. And then there's also this source J1614, which also has an independently measured mass, so that potentially could also be very interesting. And it's a little bit more massive. So I think it'll be very exciting to see what else NICER's gonna give us in the next couple of years. And then I'll slightly change topics a little bit now. So one thing that we've also investigated here is what we can actually learn from black hole neutron star mergers, not just in terms of the equation of state, but also just in terms of the binary parameters of these black hole neutron star mergers. And so I'm showing this very, I think by now quite famous plot. These are all the mergers that LIGO has detected so far. And I highlighted sort of the ones that are mostly interesting for us, looking at black hole neutron star systems. So these are potential or confirmed black hole neutron star mergers. And we've had a couple of them already. So on the left here, I'm showing the component masses of the binary of 190425, which usually is assumed to be a binary neutron star merger, but actually if you look at the posterior distribution for the high spin prior, you can actually see that the mass of the primary component is in the regime that sort of is either a very massive neutron star or a very low mass black hole. More recently, we also had 190814 here in the upper right corner, which is sort of this, could be a binary black hole, but could also be a black hole neutron star system. And then as of a few months, I think we actually have the first two confirmed black hole neutron star mergers that are right in the regime where we're quite certain it's a neutron star and a black hole just based on their masses. Unfortunately, for none of these systems, we've detected an EM counterpart. And so one of the questions that we were asking is, okay, what additional information can we gain from kilonova observations for these black hole neutron star systems? And so for this, we've been building this code that sort of tries to do both the forward modeling of likers from these systems and doing the joint parameter estimation for a gravitational wave plus EM signal system. And so the sort of general idea is that these binary properties, so the mass of the black hole, mass of the neutron star, spins, tidal deformabilities, you can connect those to some of the outflow properties that you would expect from these black hole neutron star mergers. And you do this by using sort of fitting formula to numerical simulations. Now, the thing that we wanted to capture is that for a single set of these binary properties, because you have uncertainties both in the numerical modeling and you have uncertainties in these fitting formula themselves, you will actually predict a range of these outflow properties. Now, similarly, for if you have some of these outflow properties, the mass of the ejecta and the velocity of the ejecta, you can use a semi-analytical Lie curve model to compute some Lie curves for this. But also here, there is some inherent uncertainty in the model that you use, or some parameters that you don't really know. And so each of these sets of parameters here will sort of give a range of Lie curves that you can observe. And we try to capture this uncertainty and sort of work our way through when we do this modeling. So going a little bit into these outflow properties and what they exactly are for black hole neutron star mergers. I'm seeing now that I'm missing actually that slide, but so let me keep on this slide and just briefly mention that for black hole neutron star mergers, you have to be in a very specific parameter regime to actually get some material ejected from the system. So you can either have, if for example the mass ratio is too large, the neutron star will just be swallowed whole, and you won't get any material that is ejected, so you won't actually observe any EM signals. If you have, for example, a much smaller mass ratio, then the neutron star can actually be tidally disrupted before it enters the black hole horizon. And so you get this material that is both ejected in the equatorial plane, this tidal ejecta, but you can also, so after that, the material will also form a disk around the black hole, and from this disk, you can get additional ejecta that both these components will contribute to the kilonova, and they both have different properties. One will be more blue, one will be more red, depending on the exact composition of the ejecta. And so what we wanted to do is this case study where we took 1904-25 as a sort of black hole neutron star system that could potentially be very interesting because it has a very low mass ratio. So you would expect some EM counterpart for this system. And so we simulate this gravitational wave signal very similar to this merger. And we use something called relative binning to do the gravitational wave analysis, where we basically take the ratio of some fiducial gravitational wave form. And because the ratio is quite smoothly varying over the frequency domain, you can actually evaluate your waveform at a lot less number of frequencies. So it will actually speed up your inference by a lot.
Geert, you have a minute left.
Okay, I'm nearly done. So in the plot here, we're basically showing just the gravitational wave analysis, the low and the high spin, and also the actual gravitational wave analysis for 1904-25. And so this is not that interesting actually, but I'll show this plot instead, where we also simulate some optical data according to the kilonova model that we have. And then we do the joint analysis of the signal. And what we can see then is for these three parameters, so the mass ratio, the tidal deformability, and the spin of the black hole, that we actually get a lot more constraints, especially in the tidal deformability of the neutron star, when we do this joint analysis. And so this is very interesting because this will translate to much tighter constraints on the equation of state. And so that brings me to my summary. So we've seen that nicer so far has delivered these two mass radius measurements. They both sort of point towards more stiff equation of state, so larger radii, but currently there is still all of these measurements, also in the gravitational wave signals, are quite uncertain, so we can't say too definitively anything about the microscopic behavior of matter at these extreme densities. This might change in the future. So missions like EXTP and STROBAX will hopefully fly in maybe 10 years or so and deliver much, both more mass radius measurements, but also much tighter mass radius measurements. And this can really help us pinpoint the equation of state. And then I'm also very excited about the possibility of multi-messenger gravitational wave observations, giving this very complementary method to maybe probe different parts of the equation of state, but very complementary to things like NICER and maybe STROBAX and EXTP. Yeah, and I'll stop there.